Well, welcome everybody to Lecture 4 for Chemistry 141. So we're going to start off our talk about the atom today, a little bit more of an extension into the atom, by looking at one of the first subatomic particles that we found, the electron. And the electron was discovered by a gentleman named J.J. Thomson, and he was working with cathode rays when he discovered the electron. Really all a set of cathode rays is really just a beam of electrons, and we know that now, but J.J. Thomson did not know that at the time. And what he noticed with these cathode rays is that he could deflect the beam of cathode rays with an electric or a magnetic field, and he could actually see the beam there in this glass tube. And so one of the things that he noticed is that when he was deflecting this beam is that it was repelled by a negative charge and attracted to a positive charge. And so he could deflect it using an electric field, but also he noticed that he could deflect that with a magnetic field as well. He was able to measure the charge to mass ratio based on the deflections and realized that the particles had a very, very small mass. They were around about a 1/2000th of a hydrogen atom, and that is just an estimation that he made. It's actually pretty close. But this really was interesting because it was believed for quite some time that hydrogen was the smallest possible particle. And here we have something that's much, much smaller than a hydrogen atom. And so this new particle was called an electron, and that, of course, is what we still call it today. And as we mentioned earlier, this was the first subatomic particle that was found. Now, sometime later, Robert Millikan wanted to determine the actual amount of charge on the electron. We had a rough idea of the mass, and so we wanted to determine the charge, and it turns out to have a very small amount of charge. We see it is in fact a negative charge, so we have that negative sign there, but it's 1.6 times 10 to the minus 19 coulombs, and we'll focus more on the coulombs when we do electrochemistry in the second semester of chemistry. We don't do a whole lot with it during Chemistry 141, but by combining the value that he received from the charge and Thomson's charge to mass ratio, he was able to get a much better mass of the electron, and it was found to have a mass of 9.1 times 10 to the minus 28 grams, or we also see 9.1 times 10 to the minus 31 kilograms, and so very, very small particle. And here's just a demonstration of the oil drop experiment. He had a little atomizer here. He would just spritz in some oil, very, very fine particles. You had a plate in here with a very tiny hole right in the center there, and just a couple particles at a time would be able to drop through, and he could watch those oil drops fall through, and he could balance these two, the charges on these plates to get these oil drops to remain suspended in the air. And by looking at all of the different charges that allowed him to do that, he was able to find the multiple that related back down to the mass and the charge. So now we've got to really take a new look at the atomic structure. It had been believed it was just this small indestructible sphere, and that just simply doesn't work anymore because we now have a subatomic particle there. So now we need to propose a new model to fit the new data. Again, this is kind of the scientific method in action here. And so some new models started to come out, and Thomson, since he was the one who discovered the electron, also proposed the very first atomic structure model outside of just a hard sphere. So he proposed something that's called the Plum pudding model. And the Plum pudding model was just this idea of a sphere of positive charge here with a bunch of electrons in it. It's called plum pudding because plum pudding is like a pudding with a bunch of almonds or raisins in it. So that's kind of how we saw the atom. You had this blob of positive charge with negatively charged electrons inside of it. And that actually worked fairly well for quite some time. However, as more and more experiments were done, the model began to fall apart. So as we say here, it's not a very robust model, and there was a lot of observations that it could no longer sustain. So we started needing some new models, and one of the experiments that both pretty much destroyed the last remnants of the Plum pudding model and also proposed really the model that we look at today is Ernest Rutherfords Experiments. And so what he started doing is looking at radioactivity. In the 1900s did see a very large increase in radioactivity research. And one of the things that Rutherford was doing was taking a beam of alpha particles from a radioactive alpha emitter, and he would have this beam of alpha particles that he would shoot at gold foil just to see what would happen. And they would shoot it at gold foil because gold's one of the most dense elements that we have. And so we can take a look at the model here. So we have our radioactive source in here, a lead box to prevent radioactivity from escaping in any other direction, and you would have either a very tiny slit or a pinhole here in the box that would allow a beam of highly charged alpha particles and shoot at the gold foil. And what they found for the most part is that you had very little deflection here, or a little bit there, or none there. Every once in a while you'd get something that deflected a large amount, but very unexpected is that we had deflections that were completely back off the surface of the gold foil, and that was completely unexpected. The Plum pudding model could not explain that, so they had to come up with a new version of the model. Now, if we look at this at the atomic level, and why the Plum pudding model could not account for this, the alpha particles are much more massive than an electron, and there's no way that a high-speed alpha particle could get knocked back by an electron. And so what we saw instead is the alpha particles must have been connecting with something that was fairly massive, massive enough to knock it all the way back. So Rutherford's experiments gave us a new theory about the atom. And Rutherford said, well, most of the atom's mass must be concentrated in some nucleus, and he realized that if you have this nucleus, it would give enough mass to knock back those alpha particles. However, they noticed that most of the alpha particles just went straight on through with little or no deflection when they passed through the gold foil. So the next part was most of the volume of an atom is empty space. However, if we think about atoms themselves are not charged, they have no charge. They found that electrons were negatively charged, and so there must be another particle somewhere in the atom that is positively charged. And so we called those protons. Now, even at that point, with the discovery of the proton, scientists knew that the atom was not complete. It just the protons could not account for the masses that they should have been seeing. So they realized there must be another particle present, and so it was hypothesized that the missing mass was actually in the nucleus. That would make it more massive and give it even more ability to knock back these high-speed electrons. So it wasn't until 1932 that James Chadwick actually discovered the neutron. Very difficult to find, mainly because it has no charge, so that it did not respond to any kind of magnetic or electrical field. But he was finally able to develop the techniques and the instrumentation to find it in the early 1930s. And some of the things they found out about the neutrons is that the neutron and the proton masses are nearly identical. Both are similar to the mass of a hydrogen atom, and that makes sense. So as we'll see, hydrogen atom is made up of nothing more than a proton and an electron, and so most of the mass of a hydrogen atom is really just a proton, and so the a proton being essentially the mass of the hydrogen atom and the neutron being similar, then both neutron and proton are going to be similar to the mass of a hydrogen atom. Now, when we're looking at subatomic particles, we don't always measure their masses in grams or kilograms because those are really tiny, tiny numbers. So we generally express the masses of subatomic particles in things called atomic mass units, or AMUs. And an AMU is defined as 1/12 of the mass of a carbon-12 atom. And so that's an isotope of carbon. We haven't talked about isotopes yet. So when we do charges, we often express our charges rather in coulombs. We express them in relative units. So the charge of an electron, we would say, is -1. The charge of a proton is +1. And so that's how we express our charges of our subatomic particles. And we also use those values to express charges of ions, whether they're atomic ions or polyatomic ions. And here we can look at the different masses. Here we've got our proton here with a very small mass. You can see it's got an AMU mass of just over 1. We see that the neutron, in fact, is just slightly heavier than the proton. Generally, when we're just doing our work, we consider them to have the same mass. They're the same out to 4 significant figures, or I guess they're the same at 3 significant figures and vary just slightly in the 4th. So we usually consider both of them just to have a mass of 1 AMU. We see our relative charges here, 1+ for the proton, 0 for the neutron, and -1 for the electron there. If we measure them in coulombs, you can see that the positive charge and the negative charge of the proton and electron are identical, just opposite signs there. We see the mass down here of the electron, I meant to point out and forgot, very, very small. So a lot of times when we're calculating the mass of an atom, we don't factor in the mass of the electron because it's so much less than the protons and neutrons. So if we look at elements, what we see is that all elements are composed of the exact same 3 subatomic particles. So all of the elements, all of the atoms that give us all these different properties are all made up from the same 3 ingredients: protons, neutrons, and electrons. So all subatomic particles are the same as from any other different elements, from different elements. So every proton in every element and every atom is exactly the same. All the neutrons are exactly the same. All the electrons are the same. It's just a matter of how they're put together within that element that changes the properties of those elements. So we see here a carbon proton is the same as an oxygen proton. So what makes each element different from any other element? Well, what defines the properties of the element is the number of protons that's in the nucleus. As soon as we change the number of protons in a nucleus, we actually change which element we're dealing with. And this number, the number of protons in that nucleus, is something that's called the atomic number. And a lot of times you'll see it noted as Z. So sometimes you'll see Z equals 12, and that would indicate that we have a magnesium atom. Now if we look at the periodic table, we see that the periodic table is arranged from left to right, top to bottom, by atomic number. And so it's just something to note for now. We will explore this in quite a bit more detail a little bit later in the chapter. But here's our periodic table. Just a very brief one. We see that we have the atomic number written up top. That's pretty typical. We have our chemical elemental symbol there written in the middle in very large letters. Now in this particular table they list the elemental name right there. The table that we use for class, we don't list the names there. What we do list there is something that's called the atomic mass, and that's going to be different than what we have here. So the atomic mass is a lot more useful value for us. It's different from the atomic number. let's talk a little bit about the periodic table here. So all elements are defined in the periodic table by either a 1 or 2 letter symbol. If you have an unnamed element, where up in those really large ones, they typically have three-lettered symbol in there. We saw on that table there that we have an atomic number listed up top, and that tells us the number of protons, and vice versa. If we know the number of protons, we automatically know which element we're dealing with. Some symbols, their name and symbol, are fairly intuitive. For exactly He for helium, H for hydrogen, C for carbon. However, we do have some that are a little more complex. For example, Na for sodium. The sodium doesn't even have an N or an A in it for that name. That goes back to some of the old Latin names that we had for these elements long, long ago. So sodium used to be called natrium. Iron was called ferrum, and so it has a symbol of Fe. So some of the elements and symbols are fairly intuitive, some not as much as you like. One thing we do want to point out is that you do need to make sure that you know elements 1 through 36 by symbol and name for the Unit 1 exam. We'll expand that for Unit 2. I'll give you a little bit of time to memorize those. Most of those you can probably figure out fairly easily on your own. So let's get to this idea of isotopes. When we were talking about Dalton's laws, he had said that all elements, or all atoms of the same element, are alike, and we had to say that that's actually not true. Not all atoms of the same element have the exact same mass. And we do know that all atoms of the same element have the same number of protons, because as soon as you change the number of protons, you change the element. However, it is possible for atoms of the same element to have a different number of neutrons in the nucleus. And so if they have a different number of neutrons, they will in fact have a different mass. And so we call these elements isotopes of each other. And isotopes can be man-made. We have a lot of man-made isotopes. There's also a significant number of naturally occurring isotopes for the different elements. Now, most elements have isotopes. There are just a couple that don't have naturally occurring isotopes. I should have said most elements have naturally occurring isotopes. Some do not. I think we probably got at least man-made for most of the elements in there. Well, that finishes out our lecture 4 for Chemistry 141. We'll pick up on some of this material coming up in lecture 5, continue on with our discussions of atoms there. But as always, if you have any questions on any of the content that we covered in this lecture capture, please make sure to contact your professor.